Next example of linear spanning. Show that the polynomials P1 is equal to 1 minus x plus 2x square, P2 is 3 plus x, and P3 is 5 minus x plus 4x square, P4 is this. Do not span the vector space P2. What is P2? P2 is the vector space of all polynomials of degree less than or equal to 1. So these P1, P2, P3 and P4 are the elements of P2, this capital P2. Okay, this P1, P2, P3. All these P1, P2, P3, P4 are the polynomials of degree less than or equal to 1 with real coefficient in x. Okay, so these are the elements of four elements of this P2, and we have to show these do not span the vector space P2. So when the vector spans the vector space, if every vector of that vector space expressed as a linear combination of these P1, P2, P3, P4, and when we say these P1, P2, P3, P4 do not span the vector space P2, if some element of P2 is not expressed as a linear combination of P1, P2, P3, P4, or every vector of P2 is not expressed as a linear combination of P1, P2, P3, P4. So when this P1, P2, P3, P4 span vector space P2, if every vector of P2 expressed as a linear combination of P1, P2, P3, P4. But we have to show that these P1, P2, P3, P4 do not span the vector space P2, means every vector of P2 is not expressed as a linear combination of these P1, P2, P3, P4. So we can take fx is equal to a naught plus a1x plus a2x square, where a naught, a1, a2 are scalars, is the element of this capital P2, be any element of P2. Now we have to try to express this fx as a linear combination of P1, P2, P3, P4. So let K1, K2, K3 be scalars such that fx is equal to K1 P1 plus K2 P2 plus K3 P3 plus K4 P4. That is a naught plus a1x plus a2x square is equal to K1 into substitute P1 as 1 minus x plus 2x square. Similarly P2, P3 and P4. And then apply the definition of scalar multiplication and addition. We have this, that is multiply by K1, K2, K3 in bracket, and then write the coefficient, constant coefficients, then coefficient of x square, collect the coefficient of x square and constant coefficient, and then equate the LHS and RHS. So we have K1 plus 3K2 plus 5K3 minus 5K4 is equal to a naught. In this way, the second, the coefficient of x is a1 in LHS and RHS is this, and then coefficient of x square is this, is equal to a2. And now we have to solve this system, and we have to find the values of K1, K2, K3, K4. If this system is inconsistent, then we say that this fx is not linear combination of P1, P2, P3, P4, and then we say that these P1, P2, P3, P4 do not span vector space P2, because we have the element of P2 which is not linear combination of P1, P2, P3, P4. That is, we have to show this fx is not linear combination of P1, P2, P3, P4. And when this fx is not linear combination of P1, P2, P3, P4, if this system is inconsistent. So we will solve this system by using Gauss elimination method. So form the augmented matrix. So augmented matrix is 1, 3, 5 minus 2 a naught, minus 1, minus 1, 1, minus 1, minus 2, and then 2, 0, 4, 2, a2. Okay, so this is the augmented matrix AB, combination of A and B. Okay, now we have to reduce this matrix to echelon form. So this element is 1, so we have to reduce these two element to 0. So operation are R2 plus R1 and R3 minus 2R1. So first row is this, second row is this, third row is this. Okay, then we have to reduce this 4 to 1. So 1 by 4 R2 is the application. So we have 1, 1 minus 1, and here 1 by 4 in bracket a naught plus a1. Then we have to reduce this minus 6 to 0. So R3 plus 6 R2 by using 1. So R3 plus 6 R2. So we have 0, 0, 0 at this place. And at this place we have A2. So this multiply to this by 6 and add in this. So we have A2 minus 1 half A naught plus 3 by 2 A1 after calculation. That R3 plus this plus 6 into this. Okay. And then what is the rank of A? This after by cancelling the last column, this column, The remaining matrix is the echelon form of the matrix A. And so how many non-zero rows in this matrix? This is non-zero, this is non-zero, but last row is 0. So rank of A is 2, and rank of AB, this whole matrix is the echelon form of the matrix AB, augmented matrix AB, this A oblique B. So this is the augmented echelon form of the augmented matrix. And how many non-zero rows in this matrix? This is non-zero row, this is non-zero row, this is also non-zero rows, but when if this quantity is not equal to 0. And we know that this A0, A1, A2 are any real numbers, are any scalars, and so this is not always 0. This is a non-zero for some A0, A1, A2, and this is equal to 0 for some A1, A0, A1, A2. No, this is not always 0. So this is non-zero quantity. But and if this is non-zero quantity, then we have this. If this is not equal to 0, then we have that rank of AB is 3. So in the case this quantity not equal to 0, rank of AB is 3. If A naught minus 1 half A1, A2, right? A2 minus 1 half A naught plus 3 by 2 A1 is not equal to 0. This is not equal to 0. And therefore rank of A is not equal to rank of AB. And therefore the system is inconsistent. This system is inconsistent. That is K1, K2, K3, K4 does not exist that satisfies this equation. Means Fx is not linear combination of P1, P2, P3, P4. And therefore we say that these 4 vectors do not span the vector space P2. So if you try to solve this system by Gauss elimination method, we have the condition, we have this condition, and this condition both are set. If we multiply throughout by 2, then we have this condition. So this condition and the condition obtained here both are same. So this is equal to 0. So we obtain the condition this is equal to 0, which is not satisfied for all choice of A0, A1, A2, A0, A1, A2, and therefore the system is inconsistent. So instead of this, right, this is in the after this step, right, the augmented matrix reduce the matrix to echelon form. We say system is inconsistent, and then system is inconsistent means we say that this Fx is not linear combination of P1, P2, P3, P4, and therefore we say this P1, P2, P3, P4 do not span, cannot span the vector space P2. So this is the procedure to obtain the answer. So here in R3, if S is equal to E1, E2, E3, where E1 is 1, 0, 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. Then X, Y, Z, any element of R cube is expressed as X into E1 plus Y into E2 plus, so X into 1, 0, 0 plus Y into 0, 1, 0 plus Z into 0, 0, 1 is X, Y, Z. That is every element of R3 expressed as a linear combination of E1, E2, E3. And therefore this set E1, E2, E3, suppose the set is S, then we say that S spans R3. S span R3, or we say LS is equal to R3, right? LS is equal to R3 means why when we say LS equal to R3, if every vector of R3 expressed as a linear combination of E1, E2, E3, and if you take any vector XYZ of R3, then it expressed as a linear combination of E1, E2, E3 like this, and therefore we say that this set E1, E2, E3 span R3, or LS is equal to R3. So the vector E1 is equal to, in general, E1 is equal to 1, 0, 0, 0, n tuple, E2 is 0, 1, 0, 0, and En is 0, 0, 0, n in Rn are called unit standard vectors, and this set spans Rn, because if you take U bar as U1, U2, Un is belongs to Rnb any vector, then it can be expressed as U bar as U1, E1 plus U2, E2 plus dash dash Un, En, and therefore E1, E2, En, this set spans R raised to n. So L, E1, E2, En, if this set is suppose yes, then LS is equal to Rn, or this set of E1, E2, En span Rn. Okay. Similarly, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Suppose I bar, J bar, and K bar, or E1 bar, E2 bar, and E3 bar. This spans R3. As every vector U bar of U1, U2, U3 belongs to Rn can be expressed as U bar as U1, 1, 0, 0, U2, 0, 0, 1, 0, 1, 0, and U3, 0, 0, 1, like it is said. xyz. Either take the vector of R3 as xyz or small abc or u1, u2, u3. And every vector of R3 is expressed as a linear combination of these three vectors 1, 0, 0, 0, 1, 0 and 0, 0, 1. Here the notation for these three vectors are I bar, j bar and k bar. So similarly, E1 is equal to 1, 0 and E2 is equal to 0, 1 span R2 in this fashion. Okay, and what is the set spans R raised to 4? That is E1 is 1, 0, 0, 0, 4 tuple. Then E2 is 0, 1, 0, 0. E3 is 0, 0, 1, 0. And E4 is 0, 0, 0, 1. So these four vector spans R raised to 4. So in general, E1, E2, En spans Rn. So the 1x, x square and x raised to n span the vector space Pn. What is Pn? Pn is the vector space of all polynomials of degree less than or equal to 1. Since if you take any element Px as a0 plus a1x plus an x raised to n as the element of Pn, then obviously which is a linear combination of 1x, x square, x raised to n, because we can write Px as a0 into 1 plus a1 into x plus that dash an x raised to n. That is this element as the element of Px, Pn. This Px is any element of Px, then it can be expressed as a linear combination of 1x, x square, x raised to n. And therefore, this Pn spanned by this set 1x, x square, x raised to n. Or we can say that L of this set 1x, x square, x raised to n. Suppose this set is denoted by S, then Ls is equal to Pn. Similarly, the set of matrix or the matrices E1 1 0 0 0, E2 is 0 1 0 0, E3 is 0 0 1 0, and E4 is 0 0 1 span the vector space M2 by 2R. This is the, what is this M2 by 2R? Or it is a vector space of all 2 by 2 matrices over R, means with real integers. And this four vectors spans this M2 by 2R. How we can show this is these four vectors spans M2 by 2R? We take any element, suppose capital A is equal to A, B, C, D belongs to M2 by 2R. Then it can be expressed as this A expressed as A into 1 0 0 0, that is A into E1 plus B into 0 1 0 0 plus C into 0 and plus D into 0 0 1. If we multiply this A by to this matrix, B by to this matrix, that is if we apply the definition of scalar multiplication and vector addition, then we have the if we simplify RHS, then we have the answer A, that is A, B, C, D. And so every vector of M2 by 2R, this A, B, C, D is the any vector of M2 by 2R. And this expressed as a linear combination of these E1, E2, E3, E4. And therefore we say that every vector of M2 by 2R is expressed as a linear combination of E1, E2, E3, E4. And therefore we say that E1, E2, E3, E4 span M2 by 2R. And if we denote the set E1, E2, E3, E4 by capital S, then we say that the set S span M2 by 2R. We can write that L in bracket S is equal to M2 by 2R. So this is about the spanning. So we have to write the theorem on one important theorem on the linear span. So one important theorem on the linear span. So we'll see the theorem. So theorem on this topic, linear span. So we know that when the set spans the vector space, or when the set does not span a vector space, 1x, x square spans P2. In this way, 1x, x square dash x raised to n spans P2x, or Pnx, not P2x, Pnx. Theorem is what? V is the vector space and S is the set V1, V2, Vn, that is contains n vectors from V. B set of vectors in V. So these V1, V2, Vn are the element of this capital V. Then show that LS is subspace of V, and LS is the smallest subspace of V containing S. So if we have to prove the second sentence, then in the second sentence, what is the second statement? That LS is the smallest subspace of V containing S. So we have to show first LS is a subspace of V. And so what is LS? LS is equal to, so proof, LS is equal to the set of linear combination of these V1, V2, Vn, K1, V1 plus K2, V2 plus Kn, Vn, such that K1, K2, Kn be scalars. So what is LS? LS is the set of all linear combination of these V1, V2, Vn. So K1, V1 plus K2, V2 plus Kn, Vn, such that K1, K2, Kn be scalars. So this is the definition of LS, or a linear span of S. Now we have to show LS is subspace of V. That is clearly or obviously LS is not equal to 5 and LS is subset of V. Now we have to show the two conditions for LS, that is addition of every two elements of LS belongs to LS. So let U bar and V bar, these are the two elements of LS, and obviously the U bar is what? Again, a linear combination of V1, V2, Vn. That is, take U bar as K1, V1 plus K2, V2 plus Kn, Vn, and take the another vector. It is not R, it is R, it is not R. If you take R, then take everywhere R. So this is not VR, Vn. So K1, V1 plus K2, V2 plus Kn, Vn, and take V bar as M1, V1 plus M2, V2 plus Mn, Vn. Not, it is not R, Mn, Vn. So these K's, that is K1, K2, Kn, and M1, M2, Mn are all scalars. Okay, these are all are scalars. That is, these are U bar and V bar are the elements of LS. So U bar as a linear combination of V1, V2, Vn. V bar as a linear combination of V1, V2, Vn. These scalars are not necessarily equal. So if you take K1, K2, Kn for U bar as a scalar, then for V bar, take M1, M2, Mn, or another notation. And then what is U bar plus V bar? Is K1, V1 plus K2, V2 plus Kn, Vn. Don't write R. And plus M1, V1 plus M2, V2 plus Mn, Vn as the value of V bar. And the addition is what? K1 plus M1, V1, K2 plus M2, V2, and this way plus that dash Kn plus Mn, Vn. And this, what is this RHS? RHS is the linear combination of V1, V2, Vn. This M1 plus M2, M1, K1 plus M1 is scalar, K2 plus M2 is scalar, Kn plus Mn is scalar, and so this is the linear combination. This RHS is the linear combination of V1, V2, Vn, and therefore U bar plus V bar belongs to LS for all U bar and V bar belongs to LS, because this U bar plus V bar is a linear combination of V1, V2, Vn, and therefore its U bar plus V bar belongs to LS, and this U bar and V bar are any two element of LS, and therefore we say U bar plus V bar belongs to LS for all U bar and V bar belongs to LS. Now we have to show the any vector of LS and scalar, some scalar, its multiplication belongs to LS. So U bar is equal to K1, V1 plus K2, V2 plus Kn, Vn. If we have to use R notation, then write as LS as K1, V1 plus K2, V2 plus Kr, Vr. Suppose here is notation R, then write here notation R. Here is the notation N, so don't write R notation. So let U bar as K1, V1 plus K2, V2 plus Kn, Vn belongs to LS be any element and K be any scalar. Now we have to prove the multiplication of K and U bar belongs to LS. So K into U bar is K in bracket K1, V1 plus K2, V2 plus Kn, Vn. Then multiply by K to each element in the bracket, and then write K into K1 in one bracket V1. All this because of the property of vector space, and this is K into K2, V2, K into Kn, Vn. So write R in the place of R, N, and this is the element of LS, because this RHS is the linear combination of this, as RHS is a linear combination of V1, V2, Vn, and therefore K U bar belongs to LS for all U bar belongs to LS and for any scalar K, and therefore LS is a subspace of V, because LS is non-empty, LS is subset of V, and LS satisfies the two properties, that is LS is closed for addition of every two element of LS belongs to LS, and the second condition, LS is closed for scalar multiplication, that is any vector of LS and any scalar its multiplication belongs to LS, and therefore LS is a subspace of V. Now we have to show LS is the smallest subspace containing S. So first we have to show LS contains S. So we have to show LS contains S, that is S is subset of LS, and if we take Vi as belongs to S, be any element. So S contains element V1, V2, Vn. If you take any element from this S, that is suppose Vi, then we can write Vi as 0 into V1 plus 0 into V2 plus that is 0 into Vi minus 1 plus 1 into Vi plus 0 into Vi plus 1 dash dash plus 0 into V1. That is, we can express Vi as a linear combination of V1, V2, Vn. That is, Vi expressed as a linear combination of V1, V2, Vn, and therefore Vi belongs to Vs, not Vs, LS, and therefore for all I runs from 1 to n. Right, in the place of R as n. So if we have to write the same answer, then change the question that let S is equal to V1, V2, Vr, right here R, be set of vectors in V, and then write the answer. And here correction is right here R, and then K1, K2, Kr, B scalars. Now the remaining this R now notation is clear, is correct. If we write here Er and at this place to place R, then this answer is correct now. So write V1, V2, Vr, change the theorem that S is equal to V1, V2, Vr, be set of vectors in V. And then right correction is here, right, K1, V1 plus K2, V2 plus Kr, Vr, where K1, K2, Kr, B scalars. And now this R notation now is clear, it's correct, okay? So write change the question. So if you take V1 as the element of S, for example, V1 as the element of S, then how can express V1 as 1 into V1 plus 0 into V2 plus 0 into V3 plus 0 into V1, Vn. Okay, how we can express V2? V2 as 0 into V1 plus 1 into V2 plus 0 into V3 plus that as 0 into Vn. So we can express each element of S as a linear combination of V1, V2, Vn, means Vi belongs to LS for all I runs from 1 to R. That is V1, V2, Vr, all elements of S belongs to LS, and therefore S is subset of LS, because every element of S belongs to LS. Now we have to show, this shows that S is subset of LS, means LS contains S. Now we have to show LS is the smallest subspace containing S. That is, if there is another subspace of V containing this capital S, then that is the larger than this LS. So W be any subspace of V containing S. And to prove LS is subset of W, that is LS is the smallest subspace of V containing S. Already we have shown that LS is subspace. This LS contains S. Now we have to show, it's remain to show that LS is the smallest containing S. So suppose W is subspace of this capital V containing this capital S. Now we have to show LS is subset of V. Okay, then what is then proof that LS is the smallest subspace containing S. If there is another subspace of V containing S, then it is larger than LS. That is, LS is subset of that W. So we have to show LS is subset of W, means every element of LS belongs to W. As W contains S, and W is subspace, that is W is itself a vector space, and therefore W contains all linear combination of elements of S. Because W contains S means S is subset of W, and W is subspace means W is itself a vector space, and by the property of vector space, W contains all linear combination of elements of S, and that is W contains LS. That is, LS is subset of W, because what is LS? LS is the set of all linear combinations of elements of S, and therefore LS is subset of W, and therefore we have that LS is the smallest subspace of V containing S. So hence the proof of the theorem. So as far as the exam concerned, this theorem is important, that LS is the smallest subspace of V containing S. And the next topic is linearly dependent and independent set or vectors. So we will see the definition and examples of linearly dependent and independent vectors or set